Alright, in this video we're going to step a little bit backwards to review what we had learned earlier regarding Markov chains. And in particular in this video, what we're going to focus on is on discrete state Markov chains. So a discrete state Markov chain is any Markov chain that we can represent with sort of a countable number of states that you could be in. And so the canonical example that we had before was the one of hopping between different nightlife bars or clubs or something like that. And the way we represent it is usually using something called a state diagram. So you could call this a Markov chain state diagram. And the way we represent it is each one of these nodes, for the particular example we're considering, represents a location. But a better way to think about it is a state representation of where you are. Okay? So I'm just going to label these 1, 2, 3, and 4. And what happens is you have some probability of moving from one state to another. And we represent that probability by connecting each of the nodes with arrows. And what we do is we assign a probability of going from one state to another state. So in this case, we might say if you start off at node 1, with 0.5 probability you go to node 2, and with 0.5 probability you go to node 4. For node 2, what we see is your only real option is to go to node 1 or to node 3. And so with 100% probability, you go to node 3. For node 3, we can assign, again, we're just making up probabilities here. So maybe we have a 75% chance that we go to node 1 and a 25% chance that we go to node 4. Now, node 4, I'm actually going to extend this a little bit. So I'm going to add another state. Right. And I'm going to do two things here. Right. Alright, so what I'm doing here is node 4, so let's say you're at bar number 4, you have some probability that you go to bar number 3, and so we'll put that as 0.3. There's some probability that you continue to stay at bar 3, and we'll put that as 0.5. And so in order to make sure that the probabilities sum up to 1, we know that the probability that you go to 5, state 5 is 0.2. Now in this case, what we're going to do is we're going to pretend that state 5 is like going home. Okay, so you're not going to bar hop anymore. In that case, you're going to have a self loop here that represents sort of the end of the night. You're done. And so in that case, we're going to say that that self loop has a probability 1. So what's going to happen is, let's say you go out, you're going to start off at bar 1, maybe you go to bar 4, from bar 4 you stay at bar 4, you then go to bar 3, maybe you go back to bar 4, then bar 3, then bar 1, then bar 2, bar 3, bar 1, bar 2, bar 3, bar 4, still at bar 4, and then maybe at the end of the night you go home, which is represented by number 5. And you just keep looping around and you stay there. All right, so let's sort of talk about the different sort of nodes that we have here and why we call it a discrete state Markov chain. All right, for starters, we call it a discrete state Markov chain because we can name each one of the states that you can be in. All right? When we first started our discussion of Markov chains, I discussed some Markov chains that were continuous state Markov chains. And an example of that is how long you wait for a bus. Okay, if you keep waiting for a bus, or how long does it take for each customer to arrive into a service queue? That's sort of a separate problem. In our problems, here, the state is a countable number of states. They could be infinite, okay? But we could actually name them. Okay? Now, in the how much time does it take for each customer to come, the time that it takes would be the state, in between each customer. So maybe the first customer comes after 5 minutes, the next customer comes after 10.34 minutes, the customer after that comes at 1.235 minutes. And so because the time between customers is continuous, you can't actually represent it using this type of state diagram. All right, so again, whenever you can sort of name the state that you're in, you're usually going to be talking about a discrete state Markov chain. So now let's focus in on this discrete state Markov chain. And we're going to have two types of nodes here that are of particular interest. Okay. Nodes 1 through 4 are called transient nodes. And the reason why they're called transient nodes is because as you enter them, you end up passing through them and you're allowed to leave. Now, in contrast, this node number 5 is called an absorbing node. Now, this node number 5 is called an absorbing node because the moment you enter it, you're actually not allowed to leave it because you keep looping back and forth. Okay? So you go from 5, and with probability 1, you return to 5. You can never get back to nodes 1, 2, 3, or 4 once you've entered node 5. And for that reason, we call node 5 an absorbing node. All right. Now, the next thing that I want you all to take away from this is how do we go from a state diagram into a transition probability matrix. So normally, our transition probability matrix we call P. And in this case, we're going to represent it by a matrix that is 5 by 5. Okay? So we're going to have 5 columns and 5 rows. And each value, so if I, let's say, pick out one particular value, this value we typically refer to as Pij, and it represents the probability that we go from state I to state j. And so, for example, Pij might be the probability that we go from state 1 to state 4. In that case, the Pij we're talking about would be P14. Okay. So again, Pij represents the probability of going from state I to state j. So let's actually fill out what this matrix would be for the problem that we have at hand. Right. So in this case, we know we're going to have 5 columns corresponding to the 5 states and 5 rows. And so in each row, we're going to fill in what is the probability of going from one state to another. Now, this first row is going to contain the transition probabilities leaving from state 1. Just keep in mind, sometimes we'll start numbering the states at state 0. It's all sort of the same. We're just shifting the indexing. But hopefully that doesn't confuse too many people. Okay, so let's fill out this first row for state 1. State 1 with 0 probability returns to itself, but with 0.5 probability goes to state 2. It has 0 chance of going to state 3 and state 5, but it has 0.5 probability that it goes to state 4. Next, we can do the transition probabilities for state 2. State 2 only goes to state 3. And so what we know is when we fill in this row, we're going to get 0, 0, 0, 1, and 0. Now for state 3, we have a transition to state 1 and to state 4. So that row will be given by 0.75, 0, 0, 0.25, and 0. State 4, our transition probabilities are to state 3 and to state 4. And so we have and state 5, 0, 0, 0.3, 0.5, and then with 0.2 probability, we end up going to state 5, which represents, for our problem, going home. All right. Our last row, representing state 5, we have as 0, 0, 0, 0, 1. So let's notice something interesting here. For our absorbing node, which was state 5, we see the value 1. And that's actually an indicator to us that state 5 is an absorbing node. Now, if you look at all these other nodes, they all have probabilities leaving them. Okay. That gives us an indication that these nodes here represent transient nodes. That you can pass through those nodes. Okay. So this is how we go from a discrete state Markov chain state diagram, okay, and we end up finding our transition probability matrix. Okay. So hopefully you guys found that